Picture this. You're a Bitcoiner who stores your life savings in a hardware wallet. But there's a catch. Every time you sign a transaction, the hardware wallet generates a unique number. Use the same number twice, and boom, your private key is compromised. Well, welcome to the wild world of self-custody. Today we're diving into the cryptographic rabbit hole to uncover why reusing a nonce could be your wallet's worst nightmare. Nonce is short for number used once, and it's exactly what it sounds like. A number that should be used once and only once. Before we get into the math, let's go over some background information. As some of you already know, a Bitcoin wallet doesn't actually hold Bitcoin. Instead, it safeguards your private key from the internet and signs Bitcoin transactions offline. And what about these recovery phrases? Simple, they're a human-readable form of your private key. But how exactly is this private key used in Bitcoin? This leads us to the cryptographic algorithm used in Bitcoin ECDSA. ECDSA stands for Elliptic Curve Digital Signature Algorithm. An elliptic curve is defined by an equation that looks something like this. Y squared equals x cubed plus ax plus b. In regular math, we all know that 1 plus 1 equals 2. But ECDSA plays by its own rules. It has unique definitions for addition, subtraction, and multiplication, and interestingly, no division. So when we talk about ECDSA addition, we're not talking about everyday addition like 2 plus 2. And when we mention ECDSA multiplication, we don't mean 2 times 2. Let's break it down. For addition, let's say we want to add P1 and P2. This means that P1 and P2 are both points on the curve. If we want to add these points, we have to draw a line through them. This line will always intersect the curve at a third point. We then reflect this third point across the x-axis, meaning we just take the negative of the y-coordinate, and voila, that's our sum, P3. So we say P1 plus P2 is equal to P3. Multiplication in ECDSA is simply repeated addition. We add a point to itself a specific number of times. Imagine you have a point G on the elliptic curve, and you want to multiply it by an integer private key. This means you add the point G to itself private key times. For instance, if private key equals 3, private key times G is equal to G plus G plus G. This repeated addition process is what we call multiplication in the context of elliptic curves. Let's break the multiplication rule down further. We begin with a point P on the elliptic curve. The first step is to add the point P to itself, known as doubling. To do this, we draw a tangent line to the curve at point P. This line will meet the curve at another point. We then flip this point over the x-axis to get a new point, which we call 2P. To multiply P by 3, we continue by adding 2P to P. Draw a line through 2P and P. This line will meet the curve at a third point. Flip this third point over the x-axis to get our final point, 3P. So when we say 3 times P, what we really mean is P plus P plus P, which equals 3P. Let's look at how Bitcoin uses ECDSA. Bitcoin employs a specific version of the elliptic curve called SUC P256K1. This curve defines a standard initialization point G, which is the same for all Bitcoin users. As some of you already know, your Bitcoin private key is a randomly generated number that you must keep secure. It's the ultimate key to your Bitcoin funds. Your public key, on the other hand, is derived by multiplying your private key by the point G on the curve. ECDSA multiplication has a crucial property. When we multiply point G with an integer, which is our private key, we get a new point on the ECDSA curve, which is our public key. Knowing the new point in G does not easily reveal the integer. This easy forward, hard reverse trade is common in cryptography, and is what makes ECDSA secure. The public key is, well, public. Remember the key property of elliptic curve multiplication. Knowing the multiplication results doesn't easily reveal how many times you multiplied the base point. So even with the public key out in the open, your private key remains secure. It's a one-way street, easy to go from private key to public key, but not vice versa. This public key is a point on the ECDSA curve. We use its x-coordinate and y-coordinate values to derive various Bitcoin addresses. Signature creation is another crucial feature of elliptic curve cryptography. A digital signature functions much like a real-world signature, but with enhanced security and verifiability. One key difference from a written signature is that a digital signature is intrinsically tied to the document being signed. This is because the digital signature is generated using the contents of the document. It proves the what, we call this integrity. Your signed document can't be altered without detection. Because the signature is tied to the document, if we know the original document, any changes to the document after signing would invalidate the signature. It proves the who. That's authenticity. Everyone can verify that the holder of a specific private key signed the document, because the signature can be validated using the corresponding public key. Only you can make this signature with your private key. Anyone else can check that the document hasn't been altered, and verify the digital signature to confirm it is really from you. Elliptic curve cryptography also uses a hash function for signature creation. Hashing is a process that takes an input of any arbitrary length and returns a fixed size bit string. It generates a unique fixed length output, regardless of the size of the input. This means that no matter how large the input is, the hash value will always be the same size. In Bitcoin transactions, which are created by users, the data can be short or long. This makes signing difficult. To fix this, ECDSA first hashes the transaction data before signature creation. Now that we've set the stage, let's unveil how ECDSA actually signs transactions. We first start with an integer, a private key, the number in your hardware wallet. Then we hash the Bitcoin transaction using SHA-256, creating hash HM, a neat and beautiful 256-bit number that uniquely represents the Bitcoin transaction data. To ensure each signature is unique, the algorithm introduces randomness. Here, k is a one-time random number. Using the elliptic curve algorithm, we calculate the random point r by multiplying the base point g by k. Like the public key, r is public. The relationship between k and r is similar to that of private key and public key. The key difference is that while a private key is reused, k is generated anew for each signature. Then we use this formula to create s. Rx is the x-coordinate of the random point r. This formula uses regular multiplication and addition, not elliptic curve multiplication. Note that the -1 here does not mean 1 divided by k, but the modular inverse of k. Once we have both r and s, we can combine them to form the final signature, rs, so the elliptic curve digital signature consists of two variables, r and s. Remember, r is just a random value generated by a nonce. After the signature, rs, is created, the verifier can use it along with the public key to check if the message was indeed signed by the corresponding private key, and if the message m has been tampered with or not. Let's go back to our first question. If we use the same nonce more than once, can someone figure out the private key? The answer is yes, they can. But why? Remember, in our math, the nonce is k. Now, think about what happens if someone uses the same nonce for two different messages. Let's call these messages M1 and M2. Using the same nonce means using the same k, which gives the same random point r. Because Bitcoin blockchain is public, we can easily find out the messages M1 and M2 and the signatures S1 and S2 on the internet. Since we know M1 and M2, we can compute their hash values, HM1 and HM2. Given that we know S and HM, the unknown variables are k and rx times private key. With two equations and two unknowns, we can solve this system of equations. Knowing r equals k times g, we can figure out the private key. To add an extra layer of protection to your private key, check out our tamper evident case at bitcoinserve.com.